Hello, everyone. We are the IIT Solar Scarlet Hawks next. And this is the team that has been working on our solar system design for the past 2 semesters. We are a team of both bachelor's and master's students in a variety of different engineering disciplines. Let's get into our district use case. Next, our district use case takes a look at a commercial office development in Arlington, Virginia called Crystal Parks, which consists of 5 different buildings covering 12 acres along the Potomac River. These buildings are owned by a real estate investment trust, JBG Smith, which has a long-term company goal to reduce energy, making this office development a great location for a solar installation. Next. A compilation of the 5 building load profiles is depicted in terms of both energy and power demands. The peak demands occur in August and are around 970,000 kilowatt hours and 2,200 kilowatts, just to give some context of the electrical scale we are working with in these buildings. Next, the design objectives for this district are displayed here. We looked at 3 main categories for solar installation: on-site, off-site, and fitting the former 2 with battery energy storage systems. Dominion Energy in Arlington County have a net zero by 2050 commitment, and that also aligns with our project objectives. Next, our team used an iterative approach to designing the solar arrays. We began with Aurora Solar to view irradiance models and produce monthly solar energy outputs based on the modules we placed. Next, we then ran the OpenDSS software to analyze any overload conditions by integrating the system into existing electrical infrastructure. Next, the next step was performing a financial analysis of 20-year cash flows for each project, factoring in financial considerations like degradation, depreciation, and tax credits. Next, once all of these platforms of analysis produced positive results, a development plan was put together for the installation. Next.
To determine the optimum on-site solution, we first calculated the total energy demand of the 5 buildings. Using System Advisor model, we then obtained the efficient angle and orientation to place the panels. Although the optimal tilt was obtained to be 32 degrees, it was set closer to 0 degrees. This was done to optimize the overall output, and it was done to optimize the overall output by having more panels on the rooftop. This trade-off resulted in eliminating self-shading and also increased the generation potential. Finally, Aurora Solar was utilized to model the rooftop array configuration. The roof areas that were easily accessible and unobstructed by shadows and walkways were first filled, followed by the remaining spaces. Our analysis showed that the rooftop can support more than 3,000 panels, 68 combiners, and 77 inverters with greater than 99% of solar access. The system has a capacity of 1,500 kilowatt. Next. The graph shows monthly generation profile for the on-site solution. Our annual renewable energy generation is between 200,000 to 380,000 kilowatt hour for each building. The panels offset for about 2 to 6% of yearly consumption, and they do not generate excess energy to feed the grid. Next.
We considered floating PV system as our offsite solution and chose Potomac River as a potential site location. The floating system has 3 main units: a floating structure which comprises of panels, vertical members, and body connections, a mooring system which acts as the anchor to hold the entire system in place, and an underwater cabling channel which is guided to inverters then to substation. The FPV system has several advantages, such as better efficiency, though at $1 per watt price of panels, and a natural cooling system. This system also benefits the environment around it by reducing evaporation and algae production. Next. The required area for our FPV system is approximately 88 acres. However, we were able to find around 100 acres in the river area. This is equal to whooping 76 football fields. The panels are placed with a 32-degree tilt oriented south. We use bifacial panels to utilize the reflection from water to improve the generation capacity. We haven't accounted for the reflected rays in our simulation and thus anticipate an additional benefit in terms of efficiency. Next. The annual electricity generation ranges from 1.9 million kilowatt hour to 4.4 million kilowatt hour. This satisfies the building's 100% power demand without the need for battery storage system. Next.
The basis of our battery energy storage systems was resilience. We looked at our energy provider, Dominion Energy, and determined times of the year when there is extra stress on the grid and outages are more likely. Determining that this occurs in July, we then looked at temperature characteristics to determine times of high demands of electricity, primarily for running air conditioning. Next, Looking at the battery charge graphic, the battery spends a good portion of July in a depleted charge state. Our on-site batteries are used for peak shading. The PV system only covers about 5% of the necessary electricity for the buildings. The depletion of the battery indicates electrical peaks were supplemented with this stored energy, demonstrating high electrical demands of these buildings. Next, using ROOFTOP, we ran our resilience analysis to cover between 30 to 45% of the building's critical loads in an outage to keep essential energy systems running. Next, these two graphics depict two electricity production situations, peak PV generation and peak building load. The red line shows the solar production, and clearly, even on the peak day, the array is only covering a small portion of the building's electrical demand, which was a major factor in the battery peak shading design. Next. Once we ran the REACT simulation for all of the arrays, the finances of the project were not advantageous. As you can see in the table, the net present values are negative by hundreds of thousands of dollars. Even running financially optimized simulations, REACT suggested not even including a battery energy storage system. This is because the market for electricity is very cheap in Arlington. It is difficult to implement new infrastructure and have it compete with existing cheaper options. For a battery energy storage system to financially work out, we determined two possible solutions, both anticipating future legislation for a fee on carbon-based fuels. As shown by the left graphic, the majority of Virginia's electricity is coming from natural gas, a fuel that would be affected by a carbon fee. If the prices of electricity rise by about 12% annually, the battery energy storage system will break even. This is also the case if the dollar per kilowatt hour rate of electricity increases by 5.5 times. Next.
After the designs were developed, we took a look at the load profiles of the buildings in OpenDSS to ensure that the voltage of the system is within range. Renewables introduce fluctuations in the grid. Hence, this is a crucial check to understand the viability of the design. The on-site solution data was within range. However, the off-site data overloaded the system. This indicates a need for a new substation to accommodate a grid-scale floating PV.
For our financial analysis, we used Dominion Schedule 10 pricing and calculated the average blended utility cost for all buildings. When compared with EIA's data for commercial buildings in the US, our average price was 50% lower. This resulted in some restrictions in terms of payback periods for our system designs. Next. According to our PV system size, we picked $1.83 per watt as our commercial system cost for on-site solution, and for our off-site solution, even though we found references of floating PV data internationally, we didn't find any system of this size in the US, so we picked $1.72 per watt, which aligned with our system size. To see where the system cost was heading, we developed a trend line using historical data from NREL, and we observed a 5% annual decrease. Next. We addressed the 20-year cash flow analysis by evaluating different investment tax credit and set the net present value to 0 to obtain financial parameters for making an investment recommendation. Next. For the ownership model, the required total system cost solves to 97 cents per watt for an 11-year payback period. This is a 50% lower than the current national commercial PV system cost, making it infeasible due to the limited decline observed in the trend line shown before. Next, for the developer model, we kept NREL's current commercial system cost, and we obtained a minimum PPA of $0.094 per kWh, resulting in an 11-year payback period. We observed that by increasing the PPA, the payback period reduces. So to achieve our 7-year goal, we should increase the minimum PPA at 70%, resulting in 16 cents per kWh. Next, for the offsite solution, we analyzed a virtual PPA in the same way we did it for the developer option, and ended up with similar results. Next. As a final solution, we suggest adopting a developer model with a virtual PPA that provides a 7-year payback. Examining the economic fitness of building 2011, we see that the premium cost of electricity supplied by renewable sources would be about $50,000 for the developer model, which seems like a higher price than the one JVG Smith would be paying considering Schedule 10 only. However, the developer model provides a lower risk option, allowing JVG Smith to avoid the total project construction costs that are around $500,000. Next, We also consider the installation of the offsite solution. Next, we can establish that it will be cheaper than building a new coal power plant of the same size. As we can see in the lower graph, the construction costs of the floating PV system are only bigger than one type of natural gas plant, and it constitutes a zero carbon emissions option, which we consider a more important fact.
Our rooftop development plan is divided into 6 phases, which describe site control, economic analysis meeting the state, city, and county fire code standards, county inspection, and permit process. The construction schedule is done in 3 phases, finalizing the design, procurement of equipment, and we consider buildings as one for planning and construction purposes to cut down on cost and time of procurement, permitting process, and to make the assignment of responsibilities easy. For the project site is surrounded by 3 counties, Arlington, Alexandria, and Washington, D.C. Approach was carried out using the best codes and ordinances from the documents of all 3 counties. Site analysis was done by analyzing the wetlands, historical, and floodplain data. All the results from the data showed that there were no threats to critical habitat, no flood risk, and no historical or cultural heritage sites in the designated area. Next. The location of our offsite solution is ideal because we don't easily find around 88 acres of open space in an urban district. And even if we do, there will be community curtailment, environmental restrictions, etc. This site also provides enhanced safety and security due to the presence of the airport and the jurisdiction of the 3 counties. Finally, this site is close to Crystal Parks District. According to Dominion Energy's Potomac River Substation study, one of the nearby substations faces an overload, and our project would help resolve the issue with the provision of an additional substation, which would improve the transmission and operational performance. Next.
Successful deployment of this project depends on the mitigation of safety hazards. This can be done by providing ladders and harnesses for the staff while following OSHA's guidelines. Shortage of skilled workers and a reduced supply chain of solar panels can cause a serious delay in the deployment as well. With COVID-19 lockdowns, many PV panel manufacturers are struggling to keep the production running, while some are experiencing extremely low demands. China, which is one of the biggest suppliers of this panel, has been the most hit. As their production slowly ramps up, numerous tariffs or trade restrictions that are enforced on China cause a reason for concern. Lastly, dwindling support from the government can severely halt the growth of solar industry. We need Congress to continue the ITC tax credit and allow for more incentives and rebates to take center stage. If the government continues to fund oil and gas-based system, solar will always hurt the pocketbooks. Therefore, legislation for carbon fee and dividends, such as the HR 76, need to pick momentum in Congress.
Our project outcomes matches JBG Smith's environmental objective to meet carbon and energy reduction. The project also aligns with the United Nations 2030 Sustainable Development Goals 7, 8, 11, and 13. With a generation capacity of 1,500 kilowatt, the project supports Crystal City's non-carbon energy policy, Arlington County's 2050 carbon neutrality plan, and Virginia's sustainability goals, thereby meeting city, county, and state-level green initiatives. The project would be a great opportunity to increase jobs and to invest in revitalizing communities. Next. By maximizing the energy efficiency, the project would play an important role in developing green and sustainable communities within an urban landscape. It would also open avenues for regulating climate change by avoiding carbon emissions and improving air quality. Next. To summarize, a renewable energy project like this is the need of the hour. Our recommendation would be to invest in an on-site development model with a virtual PPA of 16 cents per kilowatt hour. Thank you.